This is a stochastic processes question. It's the sort of the fundamentals of probability, essentially. So, also, actually, just to sort of remark, what I'm going to do here is I'm going to do the first part of question 1 to relate to this mouse in a maze. But you might actually be advised to watch this in full screen mode on YouTube, so you can read the question. The question is, I'll read it out here. A mouse is in a room with 4 exits at the center of a maze. Okay. Exit 1 leads outside the maze after 4 minutes. Exit 2 leads out back into the room after 2 minutes. Okay. So if you go through exit 2, you'll just, whatever way you end up, you'll just end up back at the starting point after 2 minutes. And then you have to go, the mouse has to sort of repeat the process all over again. Just try an exit. Exit 3 leads back to the room after 5 minutes, and exit 4 leads back to the room after 6 minutes. Now, every time the mouse makes a choice, it is equally likely to choose any of the 4 exits. So let's just say, for argument's sake, it doesn't have a very good, it's memoryless property of the process. It doesn't remember previous failures. Okay, it'll just keep going at random until it leaves the maze. So it just doesn't know where it is. Let t be the total time taken for the mouse to leave the maze. Find the expected time of t. Okay. Well, this actually, if you consider it, if you know, we can sort of infinitely go around in circles. Okay. We could go through exits 2, 3, 4, and 5 an infinite amount of times and never leave the maze. Or we could leave directly, we could pick exit 1 straight away and leave after 4 minutes. Okay, so what is the expected time? Okay, so it seems like it's actually quite a tough problem, or very hard to solve. And actually, you know, you'd be forgiven that. So essentially what we're going to do here is use our basic building blocks. So, of theory, so there's actually the answer. Essentially what I'm going to do here is write out a probability tree. Now, just for the sake of clarity, I've just renamed the doors A, B, C, and D. Okay, just to make it a little bit easier. Okay, A, B, C, and D, those are our 4 doors. Okay. So, these equally likely to go through each of these 4 doors. Okay. So we have a probability tree like that. I actually have a sort of very unusual way of drawing this probability tree. It just sort of suits this sort of page that I'm working on. But you might actually sort of see probability trees looking like that. But it's ultimately the same idea. So if it goes through A, it exits. If it goes through B, it ends up back at the origin. So essentially, this round circle here is the origin. Okay, the room in the middle. Okay, so that's our origin point. And if it goes, if it picks, it's 25% chance it picks route B, exit 2 in the question. It'll end back up at the origin. Likewise, C, it'll end up back at the origin, and D, it will end up back at the origin. But if it picks route A, it exits. So the black X there sort of means the exit. Okay, that's not black. In a second. There we are. So that's actually the very fundamental setup. Okay, now you're thinking, but just let's remember that. So actually what I'm going to do here is write this. The expected time is 0.25 times A. Well, correctly I should use T of A, the time taken if route A is picked, plus 0.25 B plus 0.25 C plus 0.25 D. Okay, A, B, C, and D are sort of the numeric values associated with option B, or the time for A, B, C, and D, and so on. But essentially, just as actually, let's just look at very simplistic probability trees in very simplistic terms. Probability of A, the probability of B, probability of C, the probability of D, and well, actually, correctly, I should use T of A rather than A there, just as sort of the time associated with A. Now, we'll come back to that shortly. I just want to use very fundamental ideas first off. Anyway, let's see what happens here. Let's just take this one step further. But this is just our basic building block. So what happens if we do pick route A? It takes 4 minutes and then we leave. Okay, so we go out, and it takes us 4 minutes, and we're out after 4 minutes. Okay. What happens if we go through route B? Well, it takes us 2 minutes, and we get back at the starting point. And this is the key thing here. We have to make the whole decision all over again. Okay. A, B, C, and D. Okay. Now, how long is this going to take us? Now, that seems a little bit. This might seem a little bit strange. Like mathematically, it's sound. How do we represent this in terms of time? It may seem the answer is actually very obvious. E of t. Okay. So this pink part here, essentially, mathematically, that's just 2 time units, and this what we have highlighted here, E of t. Okay. Likewise for the rest of them there, using route C, it takes us 5 minutes to get back to the origin, okay, and after that the expected time of t again, okay, and so on. You get the idea there. So that is essentially what we have here in each of these cases is we don't have to go any further with this. We can actually just mathematically state that in terms of duration as E of t. Okay. So let's just run through that again. If we're going through route A, 4 minutes. Okay. If we're going through route B, 2 plus E of t. Route C, 5 plus E of t. And route D, 6 plus E of t. So actually, it's like if now you're just thinking, hang on a minute, doesn't look so bad at all. So let's just sort of recap on this. This is something we sort of said earlier on. Okay. This is the expected time of t is 0.25 times A plus 0.25 times B. Well, correctly I should be using t of A there, t of B there, but just to sort of keep the notation quite simple, particularly if you're sort of handwriting it on these sort of documents. Okay. So what do we have here? E of t is 0.25 times 4. That is the time associated with route 4. B we said was 2 plus E of t. 2 to get back to the origin, and then E of t for the when we make the decision again, and so on. And likewise for options C and D. So that's A, B, C, and D. Okay. So when I tidy it all up, I have 0.25 times 17 plus 0.75 times E of t. You can just check that yourself, that is the answer I get there. It's just when I sort of collect up all of this, when I sort of collect it all up, I get 0.25 times 17 plus 0.75 times E of t. Or just to sort of work it out a little bit more, 17 over 4 plus 3/4 E of t. What I'm going to do here is subtract 3/4 of E of t from both sides. So I'm left with E of t over 4 equals 17 over 4. Now it looks so easy. That means necessarily that E of t is 17 minutes. Okay. So that's it in a nutshell. Now, so remember, once we sort of got past this part here, so we just sort of stated out the basics of probability in one fell swoop there. Okay, just very basic probability theories. Just sort of applied them a bit and essentially this bit about like sort of recursive usage of E of t. Once we recognized we could use that, and just make this statement here that this route B, let's say, is 2 plus E of t, piece it all together, We get a very simplistic answer. Well, not it's simplistic enough. Essentially, the key thing here was this sort of use of like EFT sort of calling itself or being part of the equation as well as the outcome. Okay, so a little bit of sort of guile was required there, but I always sort of look out for it in these sort of questions. Anyway, I think I sort of made my point that just very clever use of what you've already created mathematically helps you a lot. Okay, so that's enough of that. That is stochastic processes, mouse in a maze.